Welcome back to the CISA Exam Prep Series. So today in Domain 4, Part A, we'll focus on Information System Operation. So this is about the collection of daily processes that keep the entire business running, and because it's so fundamental, it's also a heavily weighted section of the exam. And there's certainly some fundamental technical knowledge you need to have under your belt to be an effective auditor in this area. So in this session, we'll break down all the key topics from asset management, job scheduling, we'll talk service level agreements, as well as database controls. We'll also walk through some fundamental hardware and networking concepts you need to be familiar with before we touch on incidents, problems, and changes. This domain is really all about ensuring services are stable, available, and secure. So I'll give you the specific knowledge you need, sprinkled with some real-world anecdotes and exam tips you need to understand the auditor's role for this domain on exam day. Let's get started. Domain 4 is IS operations and business resilience, and 4A will focus on the IS operations side of that equation. And while you may know me from my exam prep content here on YouTube, in my 9 to 5 I'm a cybersecurity strategist and a vCISO for a regional bank where I'm exercising my cybersecurity knowledge every day, like that which you'll find here on the CISA exam. More importantly, last year I helped thousands achieve cybersecurity certifications, like the CISSP, CCSP, and the Security Plus exams, and I'm bringing that proven formula to you here with the CISA exam. As with all my exam prep courses, you'll find a PDF copy of this presentation available for you in the video description to leverage in your exam preparation as you require. You'll also find a clickable table of contents available in the video description, and it should appear automatically on your YouTube video timeline. As I mentioned, IT operations is really about what keeps the business running, which is in part why Domain 4 is so heavily weighted on this exam at 26%, a little better than a quarter of the entire exam. So in the series here, we're going through 5 domains, 10 installments. 4A puts us at number 7. And when we look at Domain 4A, which focuses on the IS operations half of the Domain 4 subject matter, you'll see that Part A is divided into a broad range of subject matter here. We have common technology components. We're going to get into some networking basics here. We won't spend long on it because it's just an auditor's perspective. I may point you to some additional viewing there in case you're completely new. IT asset management, job scheduling, and process automation. That's a bit of a niche there. System interfaces, end-user computing, data governance, very important, systems performance management, problem and incident management, put an asterisk by that one, very important, change configuration, release and patch management, foundational and an area you should be very familiar, IT service level management, database management, kind of a technology focused area. I'm going to talk to you just a bit about how relational databases are put together, because as an auditor, you have to have a broad range of foundational knowledge. You can't be an expert in everything, but we can't assess the effectiveness of a process or a system if we don't understand it at a fundamental level. It would be like assessing the health of a nuclear reactor if you knew nothing about nuclear reactors, right? So you've got to have that foundation as an auditor. So let's start with common technology components. And I'll try to point you to the areas that I think are most likely to come up on the exam in such a broad range of subject matter. So let's talk about the OSI model, the 7 layers of the Open Systems Interconnection model. If you've taken foundational exams like Security Plus or ISC Squared's Certified in Cybersecurity, you've seen this. If you've not, I want to point out the basics to you here. So we'll start at the top of the 7 layers with the application layer. This is the user-facing interface. So we see protocols here like HTTP, FTP, SMTP, which is used for email, and their secure equivalents, HTTPS, SFTP, which as an auditor you would be interested in, right? Making sure that as you're evaluating a system that you make sure that the organization is using secure protocols. The presentation layer, there's data formatting, encryption, and compression you'd be concerned about here. The session layer that establishes, manages, and terminates connections. Layer 4, I would think, is one that would also definitely be in focus. So this is your data transfer. So we have TCP at layer 4, which is associated with reliable connections with retransmission for when getting all of the data over with absolute integrity is very important, like a data file. And then there's UDP, which is connectionless. It's associated more when we care about the real-time streaming, for example. So we'd see UDP with video streaming, right? Because retransmitting a drop packet in a live video doesn't make sense. At the network layer, this is logical addressing and routing. So here you have IP addresses, and then you have the router, the device at layer 3 that routes between IP networks or between subnets. Layer 2, the data link layer, this is physical addressing and error detection. So here we have the hardware address, also known as the MAC address or media access control address. Your switches operate at layer 2 as well. And then, of course, layer 1 is the physical layer. This is the hardware that transmits the bit. This is the wires, the cables, the hubs, etc. So for the exam, you need to understand the basic function at each layer and which devices operate at each layer. I believe if I'm looking at the 7 here, layers 3, 4, and 7 are going to be the most likely to come up. You could argue that layer 6 with encryption and compression, I think in a practical sense, a bit less likely to come up on game day. But this is really a conceptual framework for the network communications. So let's talk about key devices for a minute. So at layer 1, we have the hub or the repeater. This regenerates signals to extend network range. So I could see this coming up in the context of wireless coverage. But hubs are multi-port repeaters. I don't think we're going to see a lot there in terms of devices. Now, in terms of exam focus, layer 2. Bridges or layer 2 switches. Switches are going to be a common source of conversation because these connect network segments. They allow us to reduce our collision domains. They use MAC addresses, that hardware address at layer 2, to filter and forward frames. And I'll talk to you more about switches in just a moment. But they're hardware-based. They're going to be more efficient than bridges. They allow us to get that collision domain down to the individual ports. At layer 3, we have the router. So the router is how we separate networks. We separate IP subnets. So a router can make intelligent routing decisions based on IP addresses. So let's talk about the layer 2 switch. So we have a VLAN, or a virtual local area network. These are a common approach to segmenting a network where we logically divide a layer 2 network. And the segmentation is based on broadcast domains, where we logically group a subset of switch ports based on our communication needs. For example, we can create a VLAN for our clients, a VLAN for our servers. Typically, we'll have a separate VLAN or network for our voice over IP. Let me give you a picture here. So here's a layer 2 switch. Just a switch in a rack with a number of ports. I can set up a VLAN for, maybe these are my tablets that sit in my bank lobbies that I use with customers. And then I have a separate VLAN for my client communications. So now at layer 2, I've segregated these and I can control routing between these at layer 3 with a router. So I can allow traffic to go from that VLAN 10 where the tablets are to VLAN 20 where the client computers are using a router, or I can choose not to. I can keep those completely segmented, which reduces the blast radius of a security breach, something you'd care about as an information system auditor. So let's talk about physical network topologies. There's 3 that I believe are likely to be the most likely to come up. There's the star, where all devices connect to a central hub or switch. Switches are exceedingly common in the real world. And the star is the most common in modern lands. This is the topology that prevails today. There's the bus topology, where all devices share a single communication line, not used so much anymore. And then in a ring, devices are connected in a circular fashion. Rings haven't been popular since, I'd say, late 80s, early 1990s, if memory serves. So in a ring, only one node could communicate at a time, not terribly efficient. So that's been relegated largely to the dustbin of history. The star is the one you'll see most today. Let's talk about TCP/IP. So the suite. This is the de facto protocol suite for the internet. The internet communicates in TCP/IP. It is the language of the internet network connectivity, but it's a conceptual model. It maps to the OSI framework. TCP/IP does have its own logical model that you could map to the 7 layers of the OSI. We're not going to do that because it doesn't come up on this exam. So let's talk about IP. So remember, IP, Internet Protocol, that's what we're talking about at layer 3. You have IPv4 addresses, what you probably see most commonly today in your life, the 32-bit address. And then IPv6 is the 128-bit address, which provides a nearly infinite number of addresses. It's a fact that there are available IPv6 addresses for every grain of sand on the earth. But what you'll see today will be those 32-bit notated v4 addresses most commonly. v6 is replacing IPv4, but that's been the story for many years now, and it's just not replacing it very fast. So there are some ways that organizations can stretch their IPv4 addresses to go further because there's a limited number of those in the world. And one way to do that is through network address translation. So it converts private internal IP addresses into a public external IP address. And the benefits of using NAT are twofold. So number one, it hides your internal network infrastructure from the internet and those non-routable IP addresses from external attacks, and allows the organization to share just a few public IP addresses to access the internet, which means we're going to reduce the attack footprint and conserve IP addresses, the public routable IP addresses for the internet, which are not free. So here's a NAT server, and on the left-hand side we have the private addresses from our internal network. So there are different ranges of IP addresses that are not routable. If you look at request for comment, or RFC 1918, that defines the IP address ranges that are not routable on the internet. And that NAT server translates those to a public IP address so we can allow our end users to browse the internet safely without each having a public IP address, and it protects our applications in that respect as well. So let's talk about converged protocols for a moment in the context of TCP/IP. So this is where we merge specialized or proprietary protocols with standard TCP/IP networks. So we can run those protocols over TCP/IP, meaning we can now have multiple protocols running over a single network interface. This simplifies our infrastructure and our security. It's going to save us costs and reduce complexity. Common examples here include voice over IP, which transports voice calls over a TCP/IP network, very common in the enterprise today. And again, going back to our layer 2 discussion, that's a network that we would typically segment so it has its own private network, so to speak, to ensure the voice traffic can flow in real time as it needs to. Fiber channel over Ethernet, which encapsulates high-speed storage, fiber channel storage over Ethernet networks. That's going to be the high-performance option. The budget storage option is what we call ISACA. So it's lower cost. It allows storage devices to be accessed over a TCP/IP network. And with ISACA, I can even turn a Windows or a Linux server with a bunch of disks in it into a storage device using ISACA. MPLS is a high-performance network technology that directs data using short path labels instead of a long network address, independent of routing tables. I see MPLS in enterprise networks. It's commonly used by enterprises also to connect on-premises to their public cloud provider, to their AWS or Azure or Google cloud platform. But to give you a picture of what we're talking about with a converged network, we quite literally have that TCP/IP network, and the protocols are just running over that same network over the same Ethernet cable. Okay, so switching gears here, hardware components may come up on the exam. And the basics here should be familiar to you at this point in your career, I think. So there's the CPU, the brain of the computer that contains the arithmetic logic unit, the control unit. You have memory. You have volatile memory, which is RAM, which gets flushed over time or with a reboot. And then ROM, which is your non-volatile memory used with startup operations and others. Storage. We've got the old school hard disk drive, the HDD, which is the spinning disks. You've got SSD, which is the flash memory. It's faster, it's more durable. SSD is pervasive today. As an auditor, you're going to be concerned about hardware maintenance programs, ensuring the organization has a formal program to document and perform routine hardware maintenance according to their vendor specifications. It's also going to cover environmental hardware, power, cooling, fire suppression. So your HVAC, your generators and UPS, your fire suppression systems. And the auditor's role here is to verify a formal maintenance plan exists and is being followed. So we're not getting in the doing, you're verifying the elements of the program here. You're going to review hardware monitoring reports for availability, errors, utilization to detect problems and predict future needs. And with some types of hardware, especially with disks, for example, you can monitor for errors and spot devices that are going to fail before they catastrophically do so. So USB mass storage devices are a source of risk we want to be careful about. So portable devices that connect via a USB port are sometimes called a thumb drive or a flash drive. So there are a number of risks we need to be concerned about here. So we'll see malware. So a lot of times we see malware transmitted with these USB mass storage devices. In fact, once more common attack than it is today would be bad actors dropping a malware-laden USB drive on the parking lot of an organization. So somebody would pick that up and go plug it in to see whose drive they had just found. Data theft. It's easy for unauthorized individuals to copy large amounts of data from an unattended computer. Data and media loss. So there's a high risk of loss due to the small size, which can lead to confidentiality breaches if that device is not encrypted. And it's possible to manage your client computer so only certain types of USB devices are allowed. So you can basically lock them down to where only the devices that your organization manages and allows can be plugged into those computers and used to copy data. And you can also configure full disk encryption to basically encrypt those devices when they're plugged in. So there are certainly controls one can put in place, but encryption being first and foremost. So the data is useless without the required key or password. And if we're using something like full disk encryption, the encryption keys are stored on the motherboard of the device in what we call a TPM. Granular software, so basically blocking or managing USB ports centrally through policy like group policy or a mobile device management or endpoint management solution like Microsoft Intune or Mobile Iron or similar. But we can allow keyboards, for example, but we can block storage devices. There are policy-based controls we can use to make sure that just any old USB device is not connected to our computers. And then policy and awareness. We need to make sure that we enforce antivirus scanning and we use locked desktop policies. We educate our users so when they get up and walk away from a machine, certainly we can schedule a desktop to be locked after a certain amount of inactivity. But we want to educate our users on locking their desktops when they get up and leave. All right, let's move on to IT asset management. So this is 4A2. So this is the process of ensuring an organization's assets are accounted for, deployed, maintained, and disposed of when they're no longer needed. So from a process perspective, we have to identify all IT assets, hardware, software, and perhaps most importantly, data. It's our sensitive data that the bad actors want to steal from us and exfiltrate from the organization. We need to create and maintain an inventory of all assets. You can't protect what you don't know you have. We track the asset throughout its life cycle, which means every asset needs to have an owner that is responsible for tracking that asset and making sure that it is secure. that person is accountable. So key inventory fields we'd have would include the owner and the custodian. So the owner is ultimately accountable. The custodian would be that person to whom some of the day-to-day management responsibilities have been delegated. You can delegate responsibility. You can't delegate accountability, which ultimately comes back to that owner. The location of that asset, so we can find it if it's a physical asset. Security or risk classification. So if I have sensitive data, and I have sensitive data that I have classified as confidential, the computer or other devices from which I access that confidential data must have a like classification, and they must be secured with that in mind. Compliance requirements. Am I working with private, protected health information, for example, which means HIPAA regulations would apply? Or am I working with the personal data of residents of the European Union, where GDPR would apply? But the auditor's role here is to verify that a complete and accurate inventory of all IT assets exists and is actively maintained throughout this life cycle. Remember, you can't protect what you don't know you have. All right. Moving on to, for a 3, job scheduling and production process automation. A bit of a niche here, but reality in most enterprises today. You have batch jobs that must be run. They may run with a particular order, and any dependencies that those have, the systems or endpoints that need to be available for those jobs to succeed. The job scheduling software itself, which will vary, of course, and is secondary to our discussion here, but this is what automates the scheduling process to ensure resources are used optimally and the processes are executed consistently. The controls we're worried about here would be that high priority jobs are given optimal resource availability. We need to know that there's compute power and connectivity anytime those jobs need to run, which means we need to have eyes on the systems from which they run. Maintenance functions like backups are performed during non-peak times. We don't want resource contention by doing full backups on a system during our peak usage hours of the day. We're going to have resource contention. We'll basically be impacting disk and memory and CPU. Logs are maintained of all job successes and failures that audit trail. From an auditor perspective, you review the job schedule to ensure it aligns with business priorities, and you review the logs for evidence of job failures and timely resolution. So you're examining evidence of the underlying process there. Right. Number 4 on our list, system interfaces. So we're talking about the connections that allow data to be exchanged between different systems, both internally and with our external partners and potentially customers. So from a process perspective, we're worried about data integrity, ensuring that data is not corrupted or lost during transfer. Data confidentiality is concerned. Unauthorized access to the data in transit results in a loss of confidentiality. Data availability. Here we know that system outages can cause incomplete data transfer. So what many organizations will do with a data transfer process, for example, is to make sure that from an integrity perspective, that if I'm transmitting a file, I use a hash, a cryptographic hash, like MD5, for example, and I create a hash of that file before and after transfer to make sure that it is identical on the receiving end as it was on the sending end. From a confidentiality perspective, I'm going to encrypt that file. From an availability perspective, I'm monitoring to make sure that that link is available. So from an inventory perspective here, I'm going to use controlled totals or cryptographic hash checksums to make sure that the data sent equals the data received. That maps to integrity, right? Encryption, I'm going to protect data during transfer, especially across untrusted networks. That maps to confidentiality. And then audit trails, logging all interface activity, who sent it, when it was sent, when it was received. That confirms that availability was intact when necessary. All right, let's talk number 5 on our syllabus here, end user computing. So here we're focused on the availability of our non-IT IP professionals to design and implement their own applications. So we're thinking about folks working with spreadsheets or access databases or some form of development. Shadow IT is a problem we worry about in the world today. So that's the use of systems, services, or software without explicit approval from the IT department. For example, using a personal cloud storage account for work files. One of the earliest forms of shadow IT, unauthorized use of technology, were folks going out and starting a box account or a Dropbox account so they could trade files with whoever they needed to without having to rely on the IT department to give them resources. Or we'd see developers go out and with their corporate credit card basically spin up an Amazon AWS subscription so they could deploy virtual machines in minutes instead of waiting days or weeks for IT to get around to it for them. So monitoring for shadow IT has been a real area of focus for a lot of years. Incidentally, organizations use a cloud access security broker, or a CASB, it's called, to monitor for shadow IT. Key risks here: lack of security controls. We can't secure what we don't know is being used, right? So if there's no authorization, logging, or encryption in place, we've got an attack surface there we're not even aware of. Data loss, applications not being properly backed up. So the person using that Dropbox, what if they accidentally delete a file and maybe they're using the free tier and it doesn't have proper backup controls? We could have a problem there. Compliance violations. What if they're copying protected health information or personally identifiable information out to these unmanaged consumer-grade cloud storage accounts? That's going to be a real compliance problem that will cost an organization dearly in an audit scenario. But the auditor's role here is to evaluate the organization's policies and compensating controls for managing these risks. So if we can't with 100% reliability shut down shadow IT, what is our compensating control? Well, we monitor for use of technology that we didn't authorize. I can use my proxy server, which is natting my IP addresses. We talked about NAT earlier. A lot of times we can use our proxy server that is our gate for internet access to watch for users going to unauthorized services like a Dropbox, for example. All right, let's talk data governance. A few things I want to touch on for you here, especially if you're not terribly familiar with data security or data protection and classification. So we're focused on the overall management of availability, usability, integrity, and security of data used in an enterprise. If you were to summarize what governance means in a word, it means oversight. So overall management. So some key principles here for IS operations: ownership. Data owners have to be assigned for critical information assets. So that sensitive data needs to have an owner who is accountable for its security. Remember, they can delegate responsibility of the day-to-day management to a data custodian, but there's going to be a data owner who is accountable. Classification. So assets must be classified based on sensitivity to apply appropriate controls. The classification hierarchies will vary by organization. There's not one right answer here. So you'll see classifications from bottom to top. For example, if we think about a commercial, a non-government business, they might have public data that's publicly accessible by design, general data that's accessible to everybody within the organization, perhaps confidential data that is available to a smaller group of people, and then maybe proprietary data that represents the organization's most sensitive data. Going to vary by organization, but you're looking for a classification that basically assigns a sensitivity level to the different types of data. Integrity. So controls have to ensure data accuracy and completeness, especially in system interface and database scenarios. There's something we call referential integrity we'll talk about in the database world here in a bit. Security. So access controls, encryption, and logging have to be implemented based on the sensitivity of the data, based on its data classification. And remember, the systems used to access sensitive data need to be classified at that same level. It should match. From an auditor perspective, you're really focused on verifying that a data governance framework is in place and that operational processes like asset management, database administration, etc., follow that process, that they follow what's documented as acceptable by the organization. Right, let's move on to systems performance management, number 7 on the agenda. So the goal of system performance management is to ensure that our information system architecture, software, and just resources all up can efficiently meet current and future business demand. So our key focus areas here: operating system management, ensuring the core software that runs the computer is secure and properly configured. From a software and source code management perspective, controlling software licenses for those that we buy off the shelf and the underlying code of applications that we develop. Capacity management, so planning and monitoring computing resources, the CPU, storage, network, memory, to ensure they are sufficient, and that as we see trends where resources are growing scarce, we make a plan to update those systems so we don't have a capacity issue down the road. So the role of the operating system, it really interfaces between the user, the processor, and the software. It manages all the computer resources, right? So key concepts here. CPU is the core of the operating system. It's a highly privileged area where most user access is restricted. We'll put security controls in place to make sure that resources in privileged areas of the operating system are not just accessible to anyone. System generation, the process of customizing an OS at installation time by setting key parameters. The registry is a pretty common area of focus in the Windows world. It's kind of a file-based database of critical system configuration files and options. So it's not a database in the sense that you would think of it perhaps like an SQL server that's a relational database. The registry for Windows is actually stored in files. So from an audit perspective, you're focused on reviewing system configuration files and parameters to ensure that control options protecting the operating system's supervisory state are properly configured and secured from unauthorized changes. So what can I look at to make sure that the organization is secure? Well, I can look at a vulnerability scan. I can look at their own security software. A lot of your security suites, let's take Microsoft Defender, for example. They have what they call a secure score that will show you key vulnerabilities in an environment. So there are ways that a customer can easily show you that they are secure. They can demonstrate that they have implemented proper security through some of their own tools. Everybody should be running a vulnerability scanner periodically. Everybody should have a security suite in place for endpoint detection and response type capability, or more commonly we see extended detection and response, XDR. But there are tools you could look at to see compliance in action. So from a software licensing and source code management, so software licensing for those applications that we are buying, the commercial off-the-shelf software it's called. The license is a contract that establishes the terms under which software can be legally used. Your role as an auditor is to compare software license agreements with inventory scans to identify and report any violations, any unlicensed use, so the organization can correct that violation. If they get reported to the broader software enforcement regulating bodies, that can mean heavy fines for the organization. And then source code management for the applications the organization is developing in-house. That we're really talking about a process of managing and protecting the human readable code that makes up an application. So here we'd have a version control system software like Git. In fact, Git is the world's most widely adopted source version control system out there. Fun fact, Git was developed by Linus Torvalds, the creator of Linux. So imagine being the creator of Linux and the creator of the world's most popular version control system. Source code escrow. So this is an agreement to store the source code with a trusted third party to be released if the vendor goes out of business. So if we have an application we're working with as a customer and maybe it's customized in some way, we might arrange that agreement with the vendor to store the source code in escrow. So if we have a concern about them going out of business, should they go out of business or fail to meet their requirements in our contract, then potentially we as a customer have access to that source code so we can continue providing security updates and the like. Right. Let's talk about capacity management, the process of planning and monitoring our computing resources to ensure they sufficiently meet our business demands. So from a process perspective, we're monitoring key metrics here like CPU, storage, bandwidth, memory to make sure that utilization is within limits. What within limits means will vary by systems. We analyze trends here to establish a baseline of normal performance today so we can watch that baseline, and as resource consumption deviates, we can begin to forecast a potential growth in our future needs. We can tune systems for optimization. Certainly when we see high CPU, high network, high storage, high memory, we can look for options to tune before we go out and just buy new hardware, right? We want to try to stretch our resources further. We implement new capacity before performance is impacted. That's the goal of capacity management. It is a proactive process. So from an auditor perspective, you're reviewing the capacity plan, verifying that it is based on business input, it considers future growth, and it's updated at least annually. Somebody needs to revisit that plan on a periodic basis. Now we're going to shift gears and talk about problem and incident management. You want to be very familiar with the difference between the two. We'll take care of that right now. So we have incident management, which is a reactive process. So incident management has the primary goal of restoring normal service operation as quickly as possible. Its focus is on minimizing the immediate business impact of a disruption. Think of incident management as the fire department fighting the fire. And then we have problem management, which by comparison is a proactive process. The goal of problem management is to identify the root cause of one or more incidents to prevent them from recurring again in the future. The focus here, root cause analysis and creating a known errors database. So when we see an incident come up, we can perhaps correct it quickly and easily because we have seen it before and we have documented that in our database of known errors. Think of problem management as the fire inspector that comes in after the fire has been fought. The inspector comes in to identify the cause of the fire. So just know for the exam, you really must know the difference between these two related but very different and distinct processes. Okay, let's talk change configuration, release, and patch management briefly. So change management, the overarching process to ensure that changes are made efficiently and with a minimum of disruption to services. We've talked about change management earlier on, but you're thinking about this as an auditor, making sure there is a documented process in place. Configuration management, the process of identifying, controlling, and tracking all versions of hardware, software, and documentation. So you'll have configuration items, or CIs they're called, that identify the unique elements of hardware, software, and documentation. And remember that change and configuration management are related because when we implement a change, often we are changing the configuration. So we'll be updating our documented configuration. We will be testing and implementing those configuration changes through the change management process, where we go through and show that we have a plan to implement, we have tested those changes, and we have a plan to roll back. Release management speaks to the process of planning, scheduling, and controlling a software build through the different stages into production. So a release is a collection of authorized changes to the software. And typically today we'll have what we call continuous integration and continuous deployment. And a lot of that will be automated, but oftentimes there's going to be a manual gate before we release into production. We'll have human approval and some trip through change management to make sure everybody's on the same page. Patch management, that's a subset of change management focused on acquiring, testing, and installing code changes, patches, to address security vulnerabilities. So let's talk about the types of releases. So you have a major release, so significant new functionality here. So think of a major release as the full version number. We go from Windows 7 to Windows 8, for example. I give you Windows as an example as one most people will be familiar with. Then a minor change would have small enhancements and fixes. So I go from Windows 7 to Windows 7.1, from 7.1 to 7.2. Emergency releases are urgent fixes to prevent significant business impact. These often bypass some testing. They will increase risk. So an emergency change will often, in many environments, be pre-approved. It's something we can implement, usually with a voice approval from someone or just a simple email, and we'll go implement the emergency and come back and revisit in our change process after the fact. So key controls here: formal documented request, authorization, testing, and implementation procedures. And even for those releases that are pre-approved or automated in some respect, there will be a documented process that articulates that automated and pre-approved process. Segregation of duties, very important. So we want to have segregation of duties between development, testing, and production environments. So the same person who writes the code doesn't do all of the testing and approval themselves. We don't have one person that's developing, testing, and approving all the way to production. We have separation of duties and responsibilities there. So a critical control that you're always looking for as an auditor is a documented and tested rollback plan to restore a system to its previous state if a release fails. And in a change management process, most organizations are not going to allow a significant change to roll out unless there is a rollback plan in the change plan, in the implementation plan for that change. And many times there will be what we call rollback checkpoints or deadlines. And if we're not at a certain point of progress by a certain point in time, we know the change is catastrophically behind schedule and we will simply roll back automatically. So the auditor's role here: verify that formal change control procedures exist, they're documented, and they are followed for all types of changes. You should see that in the records kept by the change approval board, your change manager. You'll see those changes mapped over to the configuration management database, because remember, configuration and change management are closely related. Right, let's move on to IT service level management. So ITSM, this is also called. So this is a process-based approach to managing IT as a service to the business. It's often guided by frameworks like ITIL. We really hear about ITSM and ITIL in the context of the service desk or the help desk. Those are the folks that are most commonly interfacing with that process in action. They're service level agreements. This is a formal agreement between an IT service provider and a customer, which in this case might be the business, detailing the service to be provided. Now, sometimes you'll see agreements between groups on the back end, so behind the scenes, behind that SLA. So if I have a service level agreement between my database administration team and my networking team, that's called an operating level agreement. But the service level agreement is between the service provider and the customer, and it can be a pay the bills external customer, or it can be the business as the internal customer. So key components of an SLA: it describes services in non-technical business-focused terms. It defines specific measurable service levels like 99% uptime or network connectivity with a minimum of 100 megabits of bandwidth. And it includes penalties for non-performance. So just a key tip here: an organization can outsource the responsibility for service delivery. What they can't outsource is accountability for protecting their data and providing service to their customers. So making sure these SLAs are well-defined, measurable, and enforceable, very important. I think I've probably told you the story earlier in the series about a group that had a data facility hoster where they had all of their servers and their internet connectivity, and when they wanted to negotiate minimum bandwidth, the service provider said, not even a point of discussion, don't worry about, we have essentially unlimited bandwidth. And then it turned out one of their largest customers had a data center across the country that failed. All of their services failed over to this same data center. It basically bottlenecked this customer down to less than 1 megabit of network connectivity. And that service provider said, well, you didn't hold us to a minimum bandwidth, so technically we met the SLA, so we don't owe you anything. So you want to make sure these three elements are there. You need to think about what is the worst that can happen if these issues are not addressed contractually. I've just described to you a very true worst case scenario. And finally, let's talk about database management. I'm going to talk to you about some just fundamentals of relational database architecture in case you are completely unfamiliar. Because again, as an auditor, you need to have just some foundational understanding so you can spot problems. You don't need to be a database administration expert, but you need to understand the basics, right? So you can competently assess a situation. So a database management system is often abbreviated a DBMS. It's software that organizes, controls, and provides access to data. Examples here would include Oracle, Microsoft SQL Server, MariaDB, many different relational database management structures out there. That would be an RDBMS. So let's just talk about the different database structures. So you've got the relational database management system. That's the most common model today. That's Oracle, Microsoft SQL, MariaDB, PostgreSQL. So this organizes data into tables with rows and columns. I'll give you this visually in just a minute. The hierarchical or network databases, these are older tree-like or web-like structures. There's the object-oriented database. It stores data as objects. It's useful for complex data types for sure. And then there's what we call NoSQL, not only SQL. This is designed for large volumes of unstructured data. This is where we first saw the phrase big data coming into play. And there's a lot of NoSQL database varieties out there, and it's used for very large data sets. So let's talk about relational database management systems, just so you know the basic architecture of an RDBMS, because it's the most common. So we have a table. So think of a table like a spreadsheet, right? So that's the table as a whole. And we see here there's a company ID, a company name, address, city, state, etc. So the whole structure is the table. Then we have a row. That's a record in the table. And then we have a column. That's one aspect of the record. So the company ID, for example, that's the column. So in our databases, we have key control. So we strictly limit access to data based on the principle of least privilege. Oftentimes, we will not allow direct change access to the database. It can only be changed through the application interface, so we can control how the data is changed. We want to pay special attention to privileged users like the database administrator, who often has godlike powers over the database, to ensure that they are not updating that data directly in a way that will impact the integrity of the process used by the application to update that data. Integrity control. So there's something we call referential integrity that ensures relationships between tables are maintained. I'm going to show you this in a visual example in just a moment. But for example, we wouldn't want to be able to create an order in our application or on our website for a customer that doesn't exist in the customer table. And then concurrency controls. This manages simultaneous updates using techniques like record locking to prevent two users from changing the same piece of data at the same time. And then audit and logging. So database activity monitoring should be enabled, and logs should be reviewed regularly. It's a fact that logs are made valuable through review. If I collect a bunch of logs and I never look at them, they're of no value to me. They're just taking up storage. So continuing down the relational database management architecture discussion here, within that database, within that table, we have what we call a primary key. So it's selected from a set of candidates to uniquely identify the records in the table. So in that customer table, for example, the customer ID would probably be a good primary key. You're only going to have one primary key per table. It's typically set by the person who designs the database schema, who lays out the structure. And then we have another type of key called a foreign key. It's used to enforce the relationships between two tables, like that customer order relationship. This is called referential integrity. It ensures that if one table contains a foreign key, it corresponds to a still existing primary key in the other table in the relationship. Let me give you a picture here. So here's a customer table that has the customer ID. And you see there it says PK, that's the primary key. So the customer ID is the primary key. In the gift table, we have a primary key of gift ID, but you'll notice there's an FK there, a foreign key that points back to the customer, because we can't have a gift for a customer that does not exist. So the foreign key enforces the relationship between tables. It maintains that referential integrity. It ensures that if we try to create a gift for a customer ID that does not exist, it is not allowed. That's referential integrity. So some key takeaways here. Know the OSI model, especially layers 2, 3, 4, and 7, I'd say. So make sure you know key hardware, network devices. You know a switch operates at layer 2, or a router operates at layer 3. Be absolutely clear on the difference between incident and problem management. That's going to be an important one. Focus on risk and control. And for every operational process, understand the primary risks and the key controls that an auditor would look for. But think like an auditor, right? You need to know your role here. You're not responsible for designing the system. You're not responsible for operating the system. You are here to evaluate, to review, evaluate, and provide assurance, to provide confidence, which includes reviewing plans, testing controls, assessing processes. You do not perform the operational tasks. And accountability is absolutely important. Remember that accountability, the ultimate responsibility that cannot be transferred or delegated, accountability for both risk and service delivery always remains with the enterprise. They cannot delegate this away, even when they have outsourced that capability. So even when I outsource my entire data center to a hosting company, if my network bandwidth is insufficient, as I described in that nightmare scenario, I, as the enterprise, still own the outage to my external or business customers. It was still my responsibility. I failed to negotiate an enforceable SLA. Bad on me. I am still accountable. All right, my friends, that's what I have for Domain for Part A. I'll be back with Domain for B very soon in the next day or two. I hope you're getting value from the series. As always, if you have questions, drop them in the comments, ping me on LinkedIn. Happy to help anywhere I can. I'll see you back here in a couple of days, and until next time, take care and stay safe.